Okay, so good morning to everybody. Welcome to this fifth seminar of the DUS Colloquia. Today we have the pleasure. Good morning, Marika. Good morning.
Good morning, sorry.
Good morning. So today we have the pleasure to host as speaker Professor Maide Bucolo, who is giving a talk that is on a topic that is entitled Control Engineering in Two-Phase Microfluidics for Biochemical Applications. Let me spend a few words about Maide. So she is currently Associate Professor at the University of Catania. In 2010, she established and became responsible of the Biomicrofluidics Laboratory at the University of Catania. Since 2018, she is coordinator of the MSc in Automation Engineering and Control of Complex Systems at the University. So her research includes collaboration with the University of California at San Diego in the United States of America and Heliot University and the Institut National des Sciences Appliquées, sorry for my English, de Toulouse. Okay, so thanks again, Maide. Please, you can start.
So, first of all, thank all of you, to Giordano, to Marika and Elena for inviting me to giving this presentation and have the opportunity to describe the activity of the Microfluidic Lab that we started in 2010, so almost more than 10 years ago at the University of Catania. So, okay, stuck. Okay, so what we investigate, please, if there is some problem in listening me, so you cannot hear or something happen in the screen, please tell me, stop me in any moment. Okay, so what we are investigating in the Microfluidic Lab, mainly we focus our attention in two-phase flow. We can generate a two-phase flow in different conditions. The conditions that we are interested are when we have two immiscible fluid that, as we can see in the picture here on the top. This is an example of a particular regime that is called the slug flow, in which we have an interlaced sequence of the two fluids, in this case are water and air, that are passing through the microchannel. Other condition that we can have is when we have particles or cells suspended in a fluid. And this is the other example that you can see in this other video on the left corner of the slide, and which in this case there are red blood cells that are suspended in a physiological fluid. So these are the two contexts in which we move, and obviously all these processes are evolving in a microchannel. Microchannel means that, microfluidics involves processes in microchannel that are less than 1 millimeter. Generally, when we are in a diameter that is less than 100 micrometer, we are in what we call standard microfluidics. So our investigation was focusing in this range standard that is in between 100 micrometer and 1 millimeter. So we will see that the channel are mainly in the range of 300 to 600 micrometer. Why we make this choice? Because generally when we talk about two-phase flow microfluidics, we are in a nonlinear process. So the question that allows us to model the process is the Navier-Stokes equation. In the Navier-Stokes equation that is reported here, you can see that obviously we have, is described generally for a single flow. When we have a two flow, the parameter, the density and the viscosity of the fluid that are that are passing through a section in time is changing. So we have an infinite dimension problem. Infinite dimension problem, was just a cartoon on the right in which we can see an example in which we have the two input that are the two fluid that are injected in the microchannel through what we call inlet, and the process is evolving and changing in a particular area the fluid in time. So in this condition, so we have an infinite dimension problem and two input, and we have to consider the two fluid interaction that stress the process nonlinearity, the geometry of the microchannel that stress as well the process nonlinearity, and then there is another point that is the equilibrium between the viscous force and the inertial force. So what we can say that when we are below 100 micrometer, we can assume that the inertial force can be neglected, respected the viscous force. This allows a sort of linearization, at least from this aspect of the process. So to move from the Navier-Stokes equation to the Stokes equation. But in our case, that we are in the range between 100 micrometer and 1 millimeter, this cannot be applied. So this is the reason why we are on a high, we have the process that we investigate have a high nonlinearity. Why we make this choice? What can be the advantages of being in this context? The higher velocity that we can impose at the input that allow to lower the process time, because mainly the microfluidics process are the core of the device that are the lab on a chip. Lab on a chip is the standard device that is widely spreading to make the analysis of biological or sample fluid. So lower the processing time is really important. Enhance the fluid mixing and allow to have also a chemical irreversibility. So all these advantages drive us to move in this context. Which was the first problem that we have to face is in the modeling of this process, because using analytical models, so using the Navier-Stokes equation with the idea of develop a model that can be used in a real-time control in embedded device, it's, it's strictly correlated to the case of study, so that do not allow us to develop a general framework in modeling this process. So we move to the computational fluidodynamic model, but these have two problems. They lack of an analytical solution and high computational level. So no one of these can be suitable for on-chip application. That is our aim. We will see at the end of this presentation some example of device. So the idea was to move to data-driven approach. So to move to data-driven approach, we establish a platform, what we call Microfluidics engineering platform. So at the center, we have our process, so we can see our microfluidic process, and we develop around this an optomechanical setup to be able to visualize the process. And we choose to interact with the process optically, because the optic approach is the less invasive approach that we can have with the fluid and the cell that we have. So we acquire optically the information, analyze the data. This was our aim. And thanks to the information that we are able to extract from the data, so we use this information to drive to drive the actuation system. The actuation system in this case are the pump or the light as well, the laser light as well. This is an example of the experimental setup that we have used. So you can have below, you can see an example of the slug flow that are moving. So air and water in sequence are moving in this serpentine microchannel. These are the two inlet. I don't know if you can see my mouse. These are the two inlet that we feeding the process by these two. And here is the output. So we extract the fluid from the microchannel. So fine. Okay. What we feed the fluid through this hydrodynamic pump, and light the process by the laser. This is what we have, the image that we have, and we acquire the information simultaneously by two approaches: photodiode acquisition and camera. Collect the information simultaneously in a computer. Why that? Because our aim is to bring to what we develop for an embedded system in a lab on a chip application. So we want to reduce the complexity of the data that we acquire. Be able to characterize the process by optical signal, as we have in the photodiode, is much more easier than to analyze the movie and collect the data from the movie. So the video at Italy was acquired just to confirm our interpretation about the process. So this is, you can see here, there is the chip. This is all the optical mechanical system that allow us then to acquire the information in this area. We have the couple of photodiode here and the camera here. This is also a laser system that was embedded in this platform. Okay, this is what we get. So from one side, we have the video frame, and this is an example of the slug flow, because mainly I will describe all the platform that we develop based on the slug process. And then we will, in the last slide, I'll give you an idea about how this could be converted in the case of we will use the cell inside the microchannel. So in the slug flow, that is much more easy. What we have this sequence. So when we have the passage of water, we can see that the luminosity is higher. So in the signal, we can have the maximum value. Then when we have the hair, so the passage of the hair slug, we call this slug also, we have a lower level of luminosity. And then we have two peaks, the front and rear, that are for the starting, the beginning and end of the hair slug. So in this way, we are able to correlate the passage of a slug, and having a signal, we can get the information as well as in a movie. What we have noticed is that if the process became faster, this square wave trend changed in a sinusoidal trend, oscillating trend. And which is, from the point of view of the process, what is the change? That when we have this type of behavior, the length of the slug of the hair passage could be different from the length of the duration of the water slug. Instead, when the process became faster, the length of the hair and the water passage became almost equivalent. This was an example of 5 millisecond passage. So this was the first step of our investigation, which we have this match between video and signal. So the idea, it's important to make just to focus one point. When we study microfluidics, generally there is some number that are used, but these numbers are related to the input condition. These are the air fraction, the capillary number, and the Reynolds number. There are two examples. There are much more than this, but in this presentation we will use this a lot. So air fraction gives us an information about how greater is the or strong is the flow rate, the pressure that we are giving of one fluid, so the air, for example, respect to the water, at the input, so at the inlet. So we, at the inlet, we can decide to give a flow rate greater of air respect to the water, or put them equal. So it's an information related to the process, but is strictly correlated to the inlet. Then we have to the input. Another information is the capillary number. The capillary number is always all the parameters that we can see here are correlated to physical property of the fluid and the velocity of the fluid, but always at the input. And this is really important because, for example, if we have a capillary number less than 10 to the power of -2, we can confirm it to be in a particular regime that is the slug flow. We can see here an example of in the picture related to the air fraction, we have an example of the different regime that we can have. The slug flow is this one. So, and then there is the Reynolds number. a Reynolds number was defined for one flow and is adapted for the two-phase flow. Is adapted assuming as a density, viscosity, velocity, the average of the two fluids that are inside microchannel. And generally it gives us some indication about the process nonlinearity. So if we have low value of this, literature is below 1000 or 100, is depending on the context, it's strictly correlated to the context. And finally, there's the other aspect of the geometry. As you can see, it was proved that when we have a curved geometry, we create a reorganization of the particle of the fluid, so you highlight and stress the process nonlinearity. Doesn't matter which is the Reynolds number that we have. So this is just a sum up of the experiment that we carry out, because it was fundamental at this point to have a data-driven approach to investigate the process, understand the process by data, and then use this information to be embedded in a control system. So we investigate different conditions, the condition in which we, for example, don't have fluid dominance at the inlet. So we refer that like air fraction equal to 0.5 and varying the velocity of the two fluids. The blue and red arrow is representing that. The condition, for instance, in which we change the fluid dominance and varying the velocity. These are the two geometries that we considered, straight and curved geometry, and with a diameter of 300 micrometers and 600. Just to give an idea, we also move into context of flow rate with water and air flow rate less than 1 ml per minute and greater than 1 ml per minute. Why this was important? Because actually we have seen that using this diameter, it was possible to distinguish clearly slow and fast process. And this brings some difference in the analysis of data. So this is a table sum up all the conditions. So starting from that, our aim was, I wanted to be able to characterize the flow inside the microchannel. Okay, know which I'm giving at the input, but how this became the flow inside the microchannel. And the first question was, we maintain the water and air dominance inside microchannel, because when we are at a junction, this could change. So the first analysis that we implemented was very easy. We take our signal and we make a statistical histogram of the value of the occurrence of the value of this signal. So we can see, for example, the amount of value that are higher and at lower level. So, and we can distinguish in the histogram these two peaks. So the difference in height of these two peaks gives us information about how much air we have inside microchannel or how much water we have inside the microchannel. So we can evaluate computing the difference in the height of this two peaks, so that we call delta, if we have more air or more water inside microchannel. So starting from this consideration about the histogram of the signal, and we was able to develop, I mean, it's a chart that sum up this information, all the data and experimental data that we analyze. We assume initially that the air fraction at the input was equal. So at the input, I'm giving the same strength for both air and water. But what's happened inside the microchannel that I have a slow flow rate first. I mean, I have always water dominance in this context. Always water dominance. Then I have slow dynamic for flow rate that are less than 1 ml per per minute to 0.5 depending on the channel geometry, because the red line is for the straight geometry, the blue line is for the serpentine. Then I have a sort of transition zone, and then I'm moving in the fast domain, in which I have this oscillation, and obviously this fast condition is starting first from in the case of the straight geometry, and is delayed in the case of the serpentine geometry. Then what we will see is that we lose the slug behavior. This is an image to show what's happened when we lose the slug behavior. The signal is completely different, and we can see the two parallel layers of the two fluids that are running in the microchannel. So in the second, chart, we can see all the sum up of the experiment that we collected. In this case, we vary at the input the water and the air dominance. See, also on the x-axis, we have the air fraction that says that if it's less than 0.5, we have a water dominance. If it's greater than 0.5, we have air dominance. So this is what we have at the input, and this is what we can read by our parameter delta. Our parameter delta moves from positive value to negative value in percentage, and negative value because it says us that we have air dominance, positive value says us that we have water dominance. So starting from experiment in which we have water dominance, we can see that then we will have at beginning water dominance as well inside the microchannel, and this is maintained almost, it's equivalent what happened inside respect to outside for the fast dynamic. So when we have velocity greater than 1 ml per minute. Instead, when we have slow dynamic, so velocity at the input less than 1 ml per minute, we have this switch very fast. So immediately we move in a context in which inside microchannel we have air dominance. So this is proof how geometry, flow rate, and velocity, and fluid that we selected can affect and can change drastically what's happening inside microchannel respect to the condition that we are imposed at the input. So based on that, we move to another aspect. So we want to go deep on this process nonlinearity, and we focus on the condition that seems much more regular respect to the other. So the case in which the velocity is greater than 1 ml per minute. And we introduce another method to investigate the signal, because the signal is like an oscillatory signal. So we decided to analyze this signal in the frequency domain. Analyzing this signal in the frequency domain, we see that we have a band. We don't have a peak because, it's represent the variability in the oscillation. And we make an interpolation of that, and we extract the peak, and the error under this Gaussian. Thanks to these two information, we were able to collect all, analyzing all the data and what we have. We were able to say that, in this chart is sum up all the result. On the x-axis, we have always the water dominance and the air dominance represented by air fraction, and on and what we represent actually are two different variables. In the dotted line, we have the area that gives us information about how large the broadband spectrum. So the process nonlinearity increase actually when we have the maximum as here, and decrease when we have the minimum. We can see immediately the process nonlinearity decrease when we have water dominance and air dominance, and increase instead when we have a sort of equilibrium between the two fluids. So we are pumping with the same intensity, or similar, close intensity, the two fluids at the inlet. And from the other side, if we see the peak, so that give an information about how change the velocity inside the microchannel, we can see that we have a reverse behavior completely, so and it's expected. So we have faster process always for water dominance and air dominance, and instead we have a slow process when we have a sort of equilibrium between the two fluids, because the value of the peak decrease up to 30 Hertz. So here is an example of the fitting into different conditions of air fraction on the top, 0.1, 0.43, and 0.73. And what we do, we started embedding the process. And this was actually the embed that we were able to obtain. So thanks to this result, we want to stress much more that. And we know from the literature that instead of giving just a constant strength in a system, but giving a pulsatile strength, so we move to an oscillation at the input that have a sort of frequency and an amplitude, but very low for both water and air. So we use, instead of the standard syringe pump, we move to this sort of peristaltic pump. We always are in the condition with the velocity greater than 1 ml per minute, and we run a series of experiments in this condition and investigate on use the nonlinear time series analysis. So we take the signal, we make the state space reconstruction, and we, thanks to the divergence trajectory, we were able to extract the largest Lyapunov exponent. So all the experiments that we have done have been collected in this map, in which we have, this is the air frequency that we are giving at the input and the water frequency, and this is show how change in this experiment, all these experiments, the nonlinearity in terms of maximum Lyapunov exponent. And this is an example of the attractor that we can obtain, that it was a very beautiful gallery of attractor that show how this small change in the frequency, here is all the gallery, you can see we collected in a movie. This small change of the frequency was able to generate a variety of dynamic inside microchannel. So definitely the approach based on data-driven is the most suitable to do what? To develop platform. So up to that, we are enough experience about how is the process inside, and actually we have seen that there is very simple method that we can use also to quantify what's happened based on statistic and based on spectrum analysis. So we use these two types of information to realize some platform for real-time slug flow monitoring. This is the first step to realize this platform, to miniaturize this analysis for an embedded approach on a chip. So the experiment was always, I mean, we redo other type of experiment, but in any case, the experimental setup was always the same. The signal that we considered are always optical signal. The important point that instead of using one photodiode, we start to use two photodiodes close together. So we are investigating in this way in an area. Obviously, we are focusing in an area, the process in an area, but by a pair of photodiodes. So we have two signals that are for sure dilated. This is what we expected based on the process and how the process evolving. So these are the two approach that we are using, and this is the standard that I've already shown you based on the frequency. This is the spectrum of the signal, and the spectrum of the signal that give us information about the frequency, what we call, say, the frequency of the slug passage. So how a slug passage is frequent in a particular area that we are investigated. So by deeper analysis of the spectrum, we were able to detect that through this spectral analysis was possible to make also a consideration about which type of fluid are passing in this area and how change this its frequency. So we have two peaks in the spectrum. One at higher value is, a lower value is correlated to the water passage and the other to the air passage. Thanks to the two signals that we acquired simultaneously, we are performing a correlation, and thanks to the correlation we detected the delay of the two signals. Using the distance of the photodiode, we are able also to compute the velocity. It's hidden by this label, but also in the correlation function we were able to detect two peaks, and these two peaks are correlated to give us information which fluid are passing in a particular time instant under the investigation area. So this is an example. So this is for changing the velocity. In this case, we are working always with the air fraction equal to 0.5. So the strength of the air and the water flow rate at the inlet is the same. So what we have is 0.2, 0.4, 0.6, and 0.9. So we are increasing the velocity of both fluid at the inlet, and this is how it changed the signal. So from the square wave to the oscillating wave, and this is how it changed the spectrum. In this case, we have these two peaks. These two peaks, became distant, increasing the velocity. So what's happened that mainly it's, because we have this activity that is at higher frequency and the water is a low frequency, then as we can see, they are come closer, but they are come closer because also it's moving, it became faster, the water, and then we have just one peak. So the oscillation of the passage of the water and the air is synchronized and at the same frequency. So this is what I anticipated at the beginning, and now it was proved by the analysis and was able to quantify, because the power of that we can quantify that and implement in an algorithm. Exactly the same was happen in the correlation analysis. We have the two peak, one peak. So implementing this in our system, we have our syringe pump, we have our system, our flow, our process, we have the acquisition by photodiode, and we develop in LabVIEW a platform that we're able to acquire the signal, pre-processing the signal, processing the signal, and visualize the result. This is our result in three conditions. This is the graphic user interface of the platform and experiment for the channel of 640 micrometer. We are changing the flow rate at the input, you can see in this yellow area, from 0.3, 0.5, 0.4 milliliter per minute. In this square on the top, you can see the signal that we acquire from the two photodiodes, and below we have the velocity of the two fluids. Fluid 1 is air and fluid 2 is water. So we are automatically acquiring a specific time window of a specific length that we fixed, a portion of the signal, we analyze, and we get the velocity of both fluids. So you can see here 0.2, and we have the value, then it's moving to 0.5 and we have the increasing, then we are moving to 0.7 and we have another increase. The video is accelerated because the transition time, the transitory time, it's very slow in the microfluidics process, took up to a minute. So everything here that you can see is accelerated. But, and it was also not only the transition time, but also a transitory time to stabilize the process. This was the reason why we summarize, so this in this chart. You can see that we repeat different cycle for the same input condition. And we can see the velocity that we can have for the air and for the water. For the air, we have this range of velocity, and this was the velocity of the water that we can have in the input condition. So at this point, we want to have the real-time control. So we are able now to extract automatical information of what's happening inside a particular area, and we want to control that. So we want to say that if what I read is it's not exactly what I want, what I desire, I want to be able to change it. So to control by this information the pump. So from this algorithm that we call here soft-touch sensor, we establish also implement a control law, and thanks to this control law, we drive the pump, change the pump flow rate in a way that we can tune the process inside the microchannel. So this was much more complex to implement and require also a deeper awareness about the changing in the transitory time and in the approximation in the error that we can assume. But this we fix a desired frequency. We acquired the data in time windows, analyze for a certain number of cycles. As in this type of control, we implemented the spectral analysis. So we extract the peak, and thanks to the peak, we establish if the peak is the one that corresponds to the slug frequency that I desired or not. And in this case, we make an evaluation of the error and changing the flow rate. So this is our control loop. So it's the desired frequency, the delta that it was evaluated, and thanks to the control law gives us information about how much variation we need to have in the flow rate, so to driving the pump. And they give, this to the process. To do that, we actually reverse the data that we acquire. So generally, we have from one side in the x-axis the flow rate, and from the other axis the frequency. We reverse that to be able to define our control law. So in the x-axis is the frequency that we are able to detect, and based on the frequency that we are able to detect, we establish, which is the expected flow rate that we want to impose and that we have, and implement our control system. As I said, it's really important to evaluate the transient because the process is really slow, and we establish that in frequency, obviously, and also the stop condition, so the error that could be considered acceptable. So I'll show you directly the result. So in this graphic user interface, what we have here, we have as the pump as usual, and in this area we are setting our parameter. So this is for the frequency that we desire, and in the experiment that we have done, the frequency moved from 1 Hertz to 5 Hertz to 10 Hertz. So this was the frequency and all the parameters that we need to set. This is to give us information about how is the analysis and the process is going on. In the picture, we have the signal, the filtered signal, and the spectrum. So we can see how changing based on what we impose the frequency of our process. So we can, I want to start. Okay, we can see this is 10, and so you can see that the process is moving up to 10. So we can start now from the beginning. Okay. Okay, so 1, the first value, the signal acquired, and the frequency that is obtained. Then the value was 1.5. Then we move to 5. So the process now will move, changing the process, and it will stop when we reach 4.95, and you can see the change in the spectrum. And then we move to 10, and the signal are changing, the spectrum is changing, and we are stopping at 10.33. This is obviously, everything is automatic. What we are doing is just changing the desired frequency. So actually it was a good starting, I mean, more than starting point to move to the next phase of our analysis or our research, that we want to, I mean, we did all this investigation about the process, how to monitor, how to control, to be able to realize a micro-optofluidic system on a chip. So now what we want is to move all that and miniaturize all that. So the method that we are selecting, we have improved us that could be very reliable from this analysis was both. This is related to the frequency of the slug passage in the spectral domain and the slug velocity based on correlation in time domain. So thanks to this result, what we are doing, we move to the technology. So what we have now, we now know that when we want to realize a lab on a chip, we know that we need to miniaturize mechanical part, electronical part, and we have already the MEMS that are widely spread. So in this case, the problem is that we have the optomechanical setup that need to be miniaturized to be embedded in a chip, and the fluidic process. So the first step in our research, we select as a material to realize the device, the PDMS, that is widely used in biological application because it's transparent, biocompatible, good optical property, chemical property, CMOS compatible, and we can have a rapid prototype. The fabrication was the soft-lithography. So in the first step, what do we focus on miniaturize the optical part. And we have done that in collaboration with the Research Center, the CNM Centre Nacional of Microelectronics in Barcelona. And what we develop, so I have my optomechanical system, I want to miniaturize that to have some micro-optical interface. So this micro-optical interface need to be paired very easily with my microfluidic channel, and thanks to that I can acquire the photo by signal, my optical information related to the flow. So this was the first micro-optical interface that we realized, and you can see that here we are miniaturizing. The process is here. We backlight the process and acquire the optical information. Here there is a mirror. This is a waveguide that we implemented. This was some lens. And then the information is collected here by a fiber optic insertion. Here you can see the CAD of the system. It's very small. And this is just a test on the system. And was the 2 experiments that we were able to carry out using this interface. This is the interface, I don't know that you can see. And this is placed on the top of our microfluidic system in a particular area, as in the other case when we have the bulky instrumentation. So all the setup is reduced. We have just the pump, we have the chip, the light that to backlight the processing area, this interface, optical fiber that are connected in this case with a power meter. And with this very simplest optical setup, we were able to monitor the process in this area. And we did the same in an in vivo experiment in San Diego. And you can see here the process, the device is placed on the skin of an hamster to visualize and monitor the microvascular network. And these are the signal. No, we know the signal already, so it was what we expected. This was the reference signal to test, and was the signal that we are acquiring during a slug passage of air and water. And this was the signal that we acquired in this microvessel network, and compared with what we acquired by video, because we make the recording also by video and make a match. So we was encouraged by that, and we create a more complex structure in which our microfluidic chip is in like a sandwich. On the top and below I have two micro-optical interface. Thanks to this micro-optical interface that we have below, we can use 4 different wavelengths, and using this 4 different laser wavelengths, we are highlighting in a different way this area. So this red square are highlighted using 4 different wavelengths. From the other side, we collect also this information thanks to this optical structure, is another optical interface that we create, and collect it everything in one signal. So this was the experimental, a picture of an experiment. You can see here it was the side from which we highlight the process, and here is the side from which we acquire information from the process. And these are the signal. I mean, actually the signal after we post-processing. So what was really interesting that from the spectrum because we have just one signal, so we acquire one signal that embed information from 4 points. So we have a local action and a distributed action using the same device. So in one signal, I have the information about 4 points in the microchannel. And in the spectrum, these 4 points, these are the 4 frequency that we are using, the 4 wavelength that we are using for the laser, we were able to reconstruct that, and we were able to split the signal that we acquire in 4 signals that give us information about what's happening in the particular area. So, which was the limit of this approach? The limit of this approach that you can imagine that place the interface in a specific position and maintain stable all this structure. It was not, an easy procedure and needed to be overcome. To do that, we think to move and try to have, to integrate the micro-optic and microfluidic component, in what we call embedded micro-optofluidic device. Always maintaining the PDMS as a material for its advantage, but changing technology. We move from the soft-lithography to the 3D printing technology because it's low cost and offer different advantage. We are doing this also in Italy in collaboration with the CNR. And the first step was to develop a fabrication protocols, because the PDMS is a very soft material, cannot be used directly with the 3D printer up to now. So we use an approach that is a master-slave approach, in which what we have done is we create a CAD of the master. Then we make an exposition of this master by UV light, and this was an important procedure that we actually published and developed, because the material that was used from the printer cannot be in contact directly with the PDMS. So this was the limitation that we were able to overcome with this solution. So we tracked the surface of this master with this exposition to the UV light controlled in temperature. Then we fill our master with the PDMS and put in the oven. And we were able to obtain our device with not interaction with the two material surface. Very smooth. So when we developed this protocol, we started to develop the device. So our aim is now to embed the microchannel and micro-optical interface in one device. The setup, the new setup that we have in the lab, so it's changing completely, is an open setup. You can see that here there is our chip that is backlighted and connected with tubing with the pump and with the fiber optic with the laser light or the light that we want. And at the input, this is orange are the optical fiber we are using to connect with the acquisition system that could be photodiode or power meter. All this column that you can see is to have the recording by video that always is important in this case, doesn't matter if we are almost aware about our process. So this was our first micro-optofluidic device that we call micro-optofluidic flow detector. We developed that based on the principle of the total internal reflection. So from this side, we alight by laser one particular area of our chip, Then we collect information with the two fiber optic that are these two. And based on which fluid are inside, we can have reflection if we have air or transmission if we have water. This is the device. So very simple. Actually, in this case, what we have done is just create some insertion for the optical fiber. So there is no waveguide, no mirror, no lens, just insertion from the waveguide. And this is actually the picture of the device. This is the cartoon that explains the process, and this is the video. You can see from the video that the light is switched from one acquisition fiber optic to the other. We will see when the slug will change. Here is the water is coming, and we will have the switch of the light from here, from the top to below. And this is confirmed obviously in the two signal. So we can have these square waves as we expected from both optical fiber. So we can see that in one case, the switches exactly. In one case, for the optical fiber one, we have a greater number of losses in the acquisition. This is something that could be optimized by the fiber insertion. So this was the first chip, 10 centimeter and very, very nice. And then our idea is now I have to insert in this device micro-optical component. So we studied how to realize PDMS waveguide and how to realize the PDMS waveguide and pair this, for example, with mirror. So this is our two example of this. This is a mirror paired with the waveguide, and actually what we obtain is a steerer, because we were able to steer to divide the light into points. This was our aim. And this study was done also in collaboration with the Harry University, that they are using another material that is PMMA. And we did that, and this was the other device that we realized. Here you can see that is just, we are using the optical principle of absorbance, and we are, I mean, here there is the waveguide that was inserted, and it was patterned with gold, because this was important for them to maintain a difference in the refractive index of the material, to have all the light in this part. Now we overcome this passage with new technology, but at the beginning this was what we have, how we fix the problem. You can see here that actually we are able always to detect information about the slug passage, and in the paper you can find also experiment with the cell, because we were able also to detect, to distinguish the cell concentration in a specific area. And this is our last result that we obtained using this splitter, what we call light splitter. We alight 2 points, and alighting 2 points, we acquire the information in these two optical fiber, and we are able to compute the velocity. This is a very recent result, so we are going to publish that. We have to write, but it was a pleasure for me to show it. So, and it was also, we changed the technology. We don't need anymore to pattern this with gold, because we use the new material and realize this micro-optical component to insert inside the device with the new material that was with the result that was very excellent. So this is actually our last child, as we can say, in terms of device. And what's next? What's next? The next is now that we have all this device, we need to make it fix some technological problem to export all this in a system that will be portable. So we don't want to have the laptop, we want to have everything embedded in a microcontroller. So we are facing this aspect. And in doing that, we go back, but always also these aspects are fixed, to create some model of the process based on data-driven approach. So we are using wavelet and neural network. We create some some modeling to be implemented in a control predictive procedure. So this is what we are working right now, because what we want is that everything, all what we are doing, have to be coupled with the microcontroller. We are also working in using some pumps that could be smaller than this, and this is our challenge in the future. And just some few slides, because I think that I'm running the time also. Just to give an idea, what we have done with the slug flow, we are doing now, we are moving, that is the challenge right now, also in the cell flow investigation. We have some previous experience in the micro-hemodynamic lab at the USD in California, San Diego, and we have some experience about how the red blood cell moving in a fluid. And now we move everything in our lab in vitro application with different type of cell. And what we are doing, the aim is always the same. So we are acquiring video, analyzing this video using a digital particle image velocimeter, and we was already able to try to collect this information, analyze this information, and have signal, because we simultaneously acquiring always the process by signal, and make a correlation between the information that we have with image processing, that is a high computing requiring image processing, with our optical signal. We analyze the signal always in time and frequency domain. So in all this path, it was important, first of all, have a good information about digital particle image velocimeter. And these, for example, are the experiments that we have done with the red blood cell in different stress conditions, and we were able to characterize their behavior and make a classification in what we call weak behavior, vorticity, and alignment. This is based on the particle velocity that we were able to compute. And we create exactly a map for behavior classification based on the velocity that we can compute on the X and the Y axis. So this was really important to see how the cells interact among each other. So I have an idea of the collective behavior, because this strategy is aimed to investigate the collective behavior in a chip. And this was the result of our last experiment related to ELA cell 20 micrometer, EAST cell 5 micrometer, and lead cell that are synthetic cell. And we were able, by signal, this was the new result, by signal, that actually to have this type of classification. So we are able to distinguish by the signal that I'm acquiring the dimension of the cell. So if I have a live cell, I get a signal with an amplitude that moving in a range greater respect to the live cell and the bits. Just to give an idea that this could be extended also in this case. For sure will be a lot of work on that, but it's very challenging for us. So this was the application, different application that we can have. So we can cell interaction, studying cell under temperature and pressure stress. That is really important for different disease. And this is something that it was possible thanks to the PhD student and the postdoc that was in time with me, and also all the students that developed our thesis, and all the colleagues. Let me see. I mean, Professor Fortuna believed in this project first. So I think for me, it's really important always to say that, because it was the beginning. Thanks to all of you. I'm here for all your questions.
Thank you, Maide, for this interesting talk. Are there some questions? I see here Marika.
Yes, Maide, thank you very much. This is a very interesting work, really. So congratulations for what you have done. And just a curiosity about biomedical applications. I was curious about how you apply this to, you already mentioned some specific questions about, but just to be a little bit more precise.
Yes, I mean, we are in collaboration with the biological department at our university for that, to do this in deeply. And actually what we want to do is try to, sorry, let me go here that I can use that. So what we are doing, we first make the image processing, and instead of using very complex, because usually the particle image velocimeter is performed by an equipment that is highly cost. This digital particle image velocimeter allows to acquire directly from the video, the simple video acquired by camera. You can analyze that, and you can have the vector that give you the information about the particles displacement and the particle velocity. So we developed this in MATLAB, make this automatic, run an automatic algorithm to have this information that give us the orientation of the particles also. So we have the velocity, and I can say if they are moving in one direction respect to the other, for example, how is strong the displacement on the horizontal component respect to the vertical component. So simultaneously, as usual, to the video, we acquire the signal. Obviously, the signal gives us information about an average information. So our idea was to average the information that we obtain frame by frame. This was an example on the horizontal and vertical component. So we average this, and we obtain by post-processing the result of the digital particle image velocimeter. We obtain two signals, and these two signals, we create a correlation with these two signals with the one that we obtain by the photodiode. So make a correlation between these two information, we are able to face two problems. First, in some conditions, not always, okay, there are specific conditions, for example, of low concentration of particle, to overcome the problem of a video analysis, and we can move to the signal analysis to extract information about what? Especially, and this was about the cell type that we have. For example, we have seen that using the same pressure at the inlet in the microchannel, when we are using HeLa cell, for example, that are living cell actually are 16 micrometer diameter, the range of the signal is higher. Instead, when you have smaller cell, we have a range that is smaller. and is almost neglected when we have beads that are synthetic. Was a very important proof for us. And another aspect that not only the range of the signal is modified based on the nature of the cell, also the frequency, because we are always using this approach that give a small oscillation, so our pressure is not constant, we give a small oscillation. And this we have seen that is not here in the slide, but it's submitted up to now in biomicrofluidics. And we have seen that this gives us the possibility induce an oscillation in the cell, and we are able to differentiate the cell based on the resonance effect that we obtain. So I don't know if
Thank you very much. Thank you. That's very interesting, really.
Are there some other questions? So, Maide, so first of all, I was impressed of this kind of research because it involves several expertise, right?
Yes.
So there is the role of control guys, also from the biological point of view. Then there is this part related to software engineering. And I mean, it is difficult, right, to manage, no?
Yes.
Also, you were mentioning that there are many institutions, no, with whom you are collaborating to obtain, to develop this kind of research. You were mentioning, for example, Barcelona, right? And
San Diego,
San Diego.
remote universities, yes. It was important to have all this collaboration to learn, because actually it was something new for all of us in Catania. So it was really important to have this continuous exchange. And now I have to say that we are in collaboration with Toulouse. They are working in particles flow. So we are going really, we are learning from them. We have a very good exchange in this field of particles suspension. So it was really, really important, all that. But what I'm really proud is that now we are able to do this in our lab.
And
So
that's
the
great.
devices are produced in our lab.
That's great. That's great.
Yes.
Congratulations indeed. Yeah, yeah, yeah. Okay, so other questions from the audience? Just a curiosity of mine, because with Marika and Elena, we developed some results for the control of, let's say, general systems by using data. So also we are studying, you know, this data-driven control of general systems. So here in your talk, you were mentioning at least 2 times about this, right? Data-driven control, right?
Mm-hmm.
Could you please summarize, because at some time I didn't understand. So what do you mean by this? So you start collecting data, right?
Yes, actually I haven't showed this result because I mean I don't want to make every I mean.
Yeah, you have to summarize somehow, right?
Yes, I just decided in the sum up at the hand. So we used the spectral analysis and the velocity analysis for make tracking and to develop the example of the slug control in real time that we have realized. But we are thinking to a more widened approach based on the model that we realized on the web using the wavelet network and the neural network. Especially with the wavelet network, we obtain very good performance. So what we are doing, we are using this signal that we are acquiring from our experiment. We know which are the conditions of the flow rate that we have at the inlet, and obviously in some specific condition we are able to create this model, and the idea is to use this model in a predictive approach for develop some controller, real-time controller. So it will be much more so what we will realize in this way which will valid for much more experimental condition respect to the control that we have now.
Okay. Thank you, Maide.
Thanks.
Okay, so if there are no more questions, I'd like to thank you again very much for being with us today at the Use Colloquia. And okay, see Marika and Elena perhaps. And thanks again for being with us.
Thanks.
And I don't know if Marika wants to add something, and Elena also.
Thank you very much, Maide.
Thanks.
Very
Thanks for the invitation. Thanks.
Okay, so goodbye then. Have a good day.
Thank you for my presentation.
Ciao,
Thank you.
Costanza.
Oh, yeah, we have also Costanzo, yes?
Quanto tempo? Anche lui ha fatto microfluidica con me.
E non ha fatto la domanda, hai visto?
Non l'ha citato.
Perché so tutto.
Non la volevi mettere in difficoltà, diciamo
No,
così.
no.
Dai. È giusto così. Bene, bene. Ho visto anche un bel po' di gente oggi qui, eh?
Marica, sei senza microfono.
Ecco perché non la sentivo.
Parlo senza... Stavo di nuovo ringraziando. Vogliamo, per chi vuole, può accendere il video, facciamo una foto, facciamo qualche foto ricordo di questi.
Sì, dai.
Io non la so fare, però la fa Costanzo, la sa fare di sicuro,
Ma
dai.
Costanzo.
Mi dispiace che non c'ho la webcam, ma immaginate
ecco,
quanta
In
dico.
realtà la verità è che non sei
vuole
vestito in
naturalmente.
modo appropriato, secondo me.
Può essere.
Could you please, guys, switch on the camera so that we...
La cosa ogni volta è critica.
Sì, è sempre
Due
critica,
picture.
hai ragione.
Oh,
Ciao,
very
Luigi.
nice. I
Ciao.
see also Professor
Ciao Nico.
Fortuna.
Ciao Luigi, come stai?
Good morning. Oh, that's great. Okay.
Purtroppo sono senza telecamera, ma saluto a tutti. Sono Giovanni
Ciao
Rinaldi.
Ciao Giovanni.
Ciao,
Ciao
ciao a
Giovanni.
tutti. Ciao.
Piacere sentirti.
Anche per me.
Ciao Giovanni.
Allora sei sempre con
Ciao
noi,
Luigi.
anche se non sei più allo IASI, ma sei sempre con noi.
Sì, sì.
Bene, bene.
Bene.
Allora possiamo fare questa foto, anche se non tutti possono accendere la cam.
Ok, allora ci vediamo, dai.
Fatto un po',
Costanzo, io mi aspetto che tu metterai una foto mia al posto del quadratino nero dopo, eh?
Sì,
Una
Preoccupati.
cosa molto pericolosa.
Preoccupati.
Falla in bianco e nero e anche virato un po'
sì.
Costanzo.
Chiedere a Costanzo non si può fare una foto, si deve chiedere una bella caricatura. Possiamo anche spegnere tutti e Costanzo fa la caricatura di tutti, sarebbe ancora più carino.
Si può
Magari
anche
lo
fare.
utilizziamo come il nostro simbolino.
Va bene. Ho preso un po' di screenshot, poi dopo ve li passo.
Bene.
Ci autorizzate a metterli anche sul sito? Dai.
Magari, perché no? Anzi, questa è una bella idea, lo sai. Lo facciamo.
Con lo svantaggio di non vederci di persona, almeno abbiamo il vantaggio di poterci parlare 2 minuti. E quindi
Infatti.
ringraziamo di
Speriamo
nuovo
che
Maide
quest'anno
per
ci
questo
vediamo.
seminario.
Infatti.
Speriamo sì, speriamo che quest'anno sì, si possa fare.
Sì, anche
Il
basta.
CDC si farà in
Abbiamo una
presenza
prima
o in remoto
riunione in
quest'anno?
presenza adesso a marzo
Ah,
dell'IEEE, quindi può darsi che si stia avviando il processo delle conferenze di
perché mi
persona.
sembra
Chissà.
che ancora nessuna conferenza sia in presenza, almeno di quelle
Di
che
quelle
sono già
più
di
vicine
quelle più
no,
vicine.
però il CDC speriamo.
Dai.
Speriamo.
Va bene, dai.
Bene.
Grazie a
Va
tutti.
bene, allora, grazie a tutti.
Grazie ancora, Maide.
Niente, grazie a
saluto.
voi.
Lavoro.
Ciao, ciao
Ciao,
a
ciao,
tutti.
Ciao a
ciao.
tutti.
Grazie.
Ciao.
Ciao.
Ciao Giovanni. Ciao Marica. Ciao.
Ciao Luigi, ciao.